Stanford University.
All right, so we spoke a little bit about quantum fields, the quanta of the fields, creation operators, annihilation operators. We even went so far as to talk about the Hamiltonian operator for a very simple quantum field, satisfying particles satisfying the Schrodinger equation. Let me write it down. This is what it looked like. Integral over position. Now when I write dx, you don't need to imagine that it's one-dimensional. You can imagine that it's multi-dimensional, and x stands for a collection of coordinates, x, y, and z, but I'll write it as if it were one-dimensional. And then there's the quantum field psi dagger. That's the creation operator. It creates a particle at position x. And then there's a minus sign. Let's put the minus sign explicitly over here. Del squared, the second derivative operator. And if we put the mass in, the mass goes downstairs here. That's p squared over 2m. That's the standard kinetic energy of a particle. And then psi. If the particle also happens to be in a potential, if there's a potential energy, then you would add in here, and this of course is also of x, and then there's a v of x, the potential, times psi dagger of x, psi of x. And the way you would understand this term is just every particle, if it's at position x, has a potential energy v of x. Psi dagger of x times psi of x, what is that? That's the density of particles at point x. So this is just counting the number of particles at point x and giving each one an energy, a potential energy v of x. You would write that down classically too. You would write down that if you had a gas of particles and they were moving in some potential, you would write that the potential energy is the integral over all space, the density of particles at point x times the potential at that point x. Okay, so that's the Hamiltonian of a system of particles non-interacting with each other. They may be interacting with some potential. Okay, I'm going to leave out the, tell you what, yeah. Let's forget this term for a moment. No, I'll tell you what, I'm going to put it back, but I'm going to put it back v of x, and I'm going to take v of x to be a constant. Now, we all know that a constant term, potential energy, doesn't exert any forces. So it really doesn't do anything, but let's put it anyway. A constant, it doesn't matter what we call it, times psi dagger of x, psi of x. What kind of term in the energy would this correspond to? Well, it's a term which, when you integrate it over x, it just counts the total number of particles. So, if it counts the number of particles, it's just an energy proportional to the number of particles. It's giving each particle an energy. How much energy does a particle have? I'm not talking about its kinetic energy. We've already got its kinetic energy, but just a particle standing still. Does a particle standing still have any energy? Yeah, it has mc squared. So if we wanted to put that in, if we wanted to keep track of the fact that every particle has an energy mc squared, we would put it over here. But whatever it is, it's a number. The reason I want to include this here is for a very simple reason. I want to spend a minute or two talking about not energy conservation, momentum conservation. How do we see from this expression that momentum is conserved? Okay, what does it mean for momentum to be conserved? Well, what does the Hamiltonian do? What's the role of the Hamiltonian? The role of the Hamiltonian is to update the state of the system. If the state of the system at time t is psi of t, now I'm using psi to indicate a state. I better not do that. I've already used psi for several different things. One of them is for the field operator. One of them is for the single particle wave functions. I better not use it again. So let's use a different terminology for the state vector of a system. Let's not call it psi. The vector itself, let's call it phi. Right, if the state of the system at one instant of time, let's say at time t, is the vector psi of t, then what is it at the next instant of time displaced by time epsilon? Well, the answer is, that's what the Hamiltonian does. Gives you 1 minus I epsilon, that's the little time interval, little separation of time, the Hamiltonian times phi itself. Sorry, this is phi of t plus epsilon. The field, or the state at a slightly displaced time. And so what h does is it just updates things. You can write this as just phi of t. That's the same state back again. Nothing has happened. Plus a little correction after time epsilon, which is minus I epsilon times the Hamiltonian acting on phi. That's what the Hamiltonian does. And you can think of it as being iterated. You can do it over and over and over again at each step. That, of course, is another way of talking about the Schrodinger equation. The Schrodinger equation says the time derivative of phi is equal to h times phi. So that's what the Hamiltonian does. It changes the state from one instant to another. What would it mean to say that momentum is conserved? What it means is that the Hamiltonian, when it acts on a state of definite momentum, does not change the momentum. Whatever the Hamiltonian does, if it acts on a state of a given momentum, it must give back a state of the same momentum if momentum is conserved. I'm not saying it is conserved. I'm saying that's what it would mean. If the momentum is conserved, it means that when the Hamiltonian acts, it doesn't change the momentum of the system. It may change other things, but it doesn't change the momentum. Okay, we can check that. This is an interesting thing to check for this Hamiltonian. Does it change the momentum of the system? Okay, let's begin by looking at this term here. Let's forget the other term and see what it does when it acts on a state with a given total momentum. Okay, so what do we want to do? We want to rewrite this in the momentum basis. Let me remind you how that worked. That was just a good old Fourier transform. Okay, so the way that works is you say the creation operator for, this happens to be the annihilation operator, but the annihilation operator for a particle at point x is an integral over all of the momentum, the square root of 2 pi if you want to keep track of it. In fact, there's a square root of 2 pi for each direction of space. So if this were three-dimensional, there would be a 2 pi cubed, but again, this is incidental and not important. And then what we called psi twiddle, I believe, of p. This is the annihilation operator for a particle of momentum p. This annihilates a particle of momentum x. This annihilates a particle of momentum p, but then we have to multiply this by e to the I px and integrate over p. That's the creation operator x in terms of the creation operator for a particle of momentum p. Now, I'm interested in what this operator does when it acts on a state, but I'm interested in what it does to the momentum. So the natural thing to do is to rewrite this in terms of the momentum variables. So let's do that. Let's go down here. mc squared, that's just a number. And now we have integral dx. Now, each one of these can be rewritten that way. All right, so there's an integral. Let's write a second equation here. Psi dagger of x is a similar integral. I'm not going to write it as an integral of p because I've already used p. P is an integration variable. I don't want to reuse it. I don't want to recycle it. I want to use another variable. Let's call it q, dq over 2 pi. Psi dagger twiddle of q. And now there's an e to the minus I qx. Why is it e to the minus I qx? Because we're supposed to put the complex conjugate wave functions here. Everything gets complex conjugated. Okay, let's take psi of x times psi dagger of x, exactly the thing which appears here. And then let's integrate it over x and see what we get, just for fun. This is sort of fun like going to the dentist, right? Yeah, okay. So we multiply the two of these together, and we get a double integral. What's that? Is that? Yeah, okay. Okay, so we get to the dentist, and the dentist, first of all, says 1 over 2 pi. 1 over 2 pi for each direction. And then there is psi twiddle of p times psi dagger. I suppose we should put them in the opposite orders, since over here the daggers stand to the left. So let's stand the daggers to the left. Psi twiddle dagger of q, that's this one. And then psi twiddle of p. We're going to integrate over p and q in a moment, but let's first put e to the I p minus q x. That's this factor, e to the I p minus q. Question? No? Okay. And then we integrate over x. This instruction here is to integrate over x. Okay. Does anybody remember what you get when you integrate e to the I something times x over x? A delta function. Now, the way, if you forget that, the way to think about it is the following. Supposing p minus q is not 0, then this is an oscillating thing. If p minus q is not 0, then it oscillates with x. What happens if you integrate something which oscillates as much positive as negative?
dq.
Yeah, sorry, dp dq. Good.
Yeah, it just depends on the nature of the oscillation, but if it's all symmetric, then it
That's right.
cancels out.
This is a mnemonic. This is not a rigorous argument. But if p is not equal to q, it oscillates. It has a sine in it, a cosine in it. The sines and cosines are as positive as they are negative, and that must integrate to 0. On the other hand, if p is equal to q, then this is just 1. And the integral of 1 over all space is infinite. So this is a function of p minus q, which is 0 if p minus q is not 0. In other words, if p is not equal to q. And it's infinite if p equals q. Obviously, this is proportional to the Dirac delta function, and with the 2 pi there, it is the Dirac delta function. So this all becomes, we can erase the e to the I p minus q, erase the integral dx, and just write that this is delta of p minus q. And we also get rid of the 1 over 2 pi. Okay, what happens if we integrate psi dagger of q times psi of p with a function which is 0 unless p is equal to q? Well, it's just the instruction. Do the integral, but set p equal to q. If you set p equal to q, there's only one integration, And this is just equal to psi dagger twiddle of q. Let's write it as p. The instruction here is set q equal to p. So this is p psi of p. Okay, now what do we have here? We have an operator which contains a destruction operator or an annihilation operator times a creation operator. It's an annihilation operator for a particle of momentum p. So if it finds a particle of momentum p, it pulls it out and kills it, it annihilates it. But then it puts back a particle of the same momentum. Notice, here was the important thing, that by the time you finished, P had to equal Q. P had to equal Q tells you that if you remove a particle, you put back a particle of the same momentum, and the momentum doesn't change when this operator operates on a state. It does not change the momentum. Whatever it takes out, it puts back. Okay. What was the working ingredient here? It was the integral over x which turned this into a delta function. Okay. The integral over x turned it into a delta function, and the delta function, you can say, was the delta function of momentum conservation. Momentum, that when the Hamiltonian acts, when it updates the state a little bit, we somehow no longer have the updating of the state, but when it updates the state a little bit, it doesn't change the momentum. Okay. Now, we can go, we could do the same thing with this term here. Let's do it. Let's go through it, just so that you see how the machinery works.
Quick question, please.
Yeah.
What happened to that being infinite when p is equal to q? Somehow we don't talk about it.
No, that's okay. Whenever you integrate a Dirac delta function with another function, you just get that function at point 0. That's the definition of the Dirac delta function. The fact that it's infinite but of 0 width. See, it's a thing which is infinitely high but infinitely narrow. The area under it is 1 unit. Okay, so it doesn't give anything infinite, it just gives back. And in this case, it just tells you set p minus q equal to 0, which is the same thing as setting p equal to q. Okay, before I look at this term here, let me just point out that this could be more general. Let's suppose we had a term in the Hamiltonian which had, for whatever reason, for reasons that we'll talk about later, we had a whole bunch of fields. They could even be fields for different kinds of particles. Creation operator and annihilation operator for different kinds of particles. And instead of having just 2 of them, we could imagine in the Hamiltonian, and we'll discuss what this means, that we could have any number of psi daggers, a particle of type A, particle of type B, any number of psis, particle of type C, particle of type D. They could all be the same or not the same. Any number of psi daggers and any number of psis. Suppose in some insane world we put this thing into the Hamiltonian. What would happen? Well, instead of getting what we have up here, the simple expression, what we would have is a whole bunch of integrals, a p integration for each field that appears here. Let's, whole bunches of p's. The p's could stand for the half of the particles that are being created, for example, dp1, dp2, dp3, and so forth, however many particles or however many fields there are with dagger. And then, oh no, those are q's, sorry. Q's go with the daggers, p's go with the psis. All right, so we have some q's also, dq1, however many of those there are. And then we have a bunch of creation and annihilation operators of exactly the same kind, except many of them now. Side dagger of P1, or side twiddle of P1, dot, dot, dot. Psi daggers, size of Q's, Q1, dot, dot, dot. But then the all-important exponentials. The all-important exponentials, and they read for each psi, let's see, for each, I think I did it wrong again, QP, if I wanted to follow the same notation up there, P. Then I would have an e to the I, and then for each P, P1 plus P2 plus P3, all times x. Each one would come in with its own e to the I px, and you'd add them all up in the exponent. But then you'd also have minus I q1 plus q2 dot, 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 x. In other words, instead of just having a single p and a single q, you would have a bunch of p's for all the creation operators. Is it which ones get the p's? P's go with the annihilation operators, and q's go with the creation operators. Okay, and you have to integrate it over x. You have to integrate it over x. What does the integration over x give you? Again, it gives you a delta function, and it's a delta function of the sum of all the p's minus the sum of all the q's. In other words, it's a rule that the sum of the p's has to be equal to the sum of the q's. The sum of the p's is all the particles that you take out, the things with the annihilation operators. The sum of the p's is all of the momentum of the particles that you put in. So it's just a rule. It says, the rule just says the total momentum of the particles that you take out must equal the total momentum of the particles that you put back. It's a rule that follows from this kind of Hamiltonian here. Now, what's really going on is the fact that this Hamiltonian is translation invariant, but I wanted to show you how the machinery works. And so whenever you see a Hamiltonian of this form, that it has a whole bunch of psis and psi daggers, but you integrate it over space. It's the integral over space which gives you the delta function. It's the integral over space which says momentum conservation, momentum conservation, momentum conservation. It doesn't say that that P1 should be equal to Q1 and P2 should equal Q2. It says the sum of all the incoming momentum should be the same as the sum of all the outgoing momentum. Okay, so that's momentum conservation.
In the Hamiltonian, that's the product of all those field operators?
Yeah, product of all these field operators. Why would you do that? We'll come to why you might do that. Not why you might, why this is one of the central points of quantum field theory. But before we do it, let's take this term in the Hamiltonian over here. This has the additional derivatives. Let's go back and ask what would happen to this calculation, the first, the original one here, if we changed it by differentiating with minus del squared the psi dagger. Before we multiply it with psi, what does minus del squared, this is just a second derivative, what does it do when it hits here? Well, to know, we just go over to this side. Let's differentiate this side twice with x. What depends on x? Well, dq doesn't depend on x. 2 pi doesn't depend on x. In fact, psi dagger doesn't depend on x. The only thing that depends on x are these oscillating wave functions here. So what happens if you differentiate twice the oscillation here? Q squared plus q squared. Minus iq times minus iq. So this would give us q squared. In other words, the square of the momentum of the particle that you're creating here.
Isn't it minus?
No.
That's why.
There's a
No,
minus.
it's,
Minus an I squared.
Look at the far left side of the equation, there's a minus sign.
there's a minus here, and then a minus,
I didn't see that.
no, right.
Thank you.
There's a minus here, that's why there's, well, this minus is here because that's what goes in the Hamiltonian, but, yeah. Okay, so what's the upshot? The upshot is the same kind of expression that we had before. Again, you get to integrate e to the I p minus qx. It's again going to give you our momentum conservation. But instead of just having integral side dagger twiddle of p times psi twiddle of p, that just counted the total number of particles of each momentum and added them up. There's another factor of p squared. It's this thing here, which when you use the delta function, just gives you p squared. What is this thing giving you? First of all, it conserves momentum. The momentum in and the momentum out have to be the same for exactly the same reason, but it's just weighing each particle with the square of its momentum. In other words, it's counting the kinetic energy of each particle. It's just adding up all the particles, adding up the number operator for each momentum, and multiplying it by p squared. I suppose, where's the 2m? We left out the 2m. P squared over 2m. So it's doing exactly what it's supposed to do. It's counting up the kinetic energy of the particles, and momentum is conserved because of the delta function. Okay, let me show you an example of an interesting term that you could put into the Hamiltonian. Let's suppose you had two species of particles. Let's call one an electron and the other a proton. The species. Now, I'm cheating because if I really wanted to do electrons and protons, I wouldn't be doing boson operators. Okay, so these are fake electrons and protons which happen to be bosons. Let's forget the MC squared term. No, we're not going to worry about the MC squared term. What's that?
In the conservation of energy, kinetic energy,
Yeah.
that's only in the case when there's
Kinetic energy, or we want momentum or energy?
kinetic energy.
Kinetic energy, yes.
That's only true in the case where the potential energy is constant.
We haven't put any, yeah, exactly, yes, so. That is so. That is a true statement.
What is the interpretation of the side dagger in the Hamiltonian?
It counts. Psi times psi dagger is a counting operator. In this case, it's counting the number of particles with each momentum and multiplying by p squared.
No, he didn't see the multiplication there.
Oh, okay, good. Yeah. You know, there's another trick you can do. This thing looks negative, doesn't it? But of course, everybody knows the kinetic energy of a particle is positive. So what's going on? Well, everybody know how to integrate by parts. If you have psi dagger of x, and you have two derivatives with a minus sign, d by dx times d by dx times psi. I'm not going to work this out in detail. I'm going to tell you the result. The d by dx's both act to the right. They act on psi. Integration by parts allows you to take one of these derivatives and shift it to the other side. In fact, integration by parts would allow you to take both of them and shift them to the other side. But I don't want to shift both of them. I just want to shift one of them. But what do you have to do when you integrate by parts in addition to taking the derivative and shifting it to the other factor?
Change the sign.
Change the sign. You also have to worry about edge effects, but you know, we won't worry about that now. So you can rewrite this as d by dx of psi dagger times d by dx of psi. And now this is just a square of something, and it's positive. Integrated dx. That's kind of interesting to see in the Hamiltonian the square of the derivative of psi. It's very much like any other field theory where what you see in the Hamiltonian is squares of derivatives of the fields. Okay? In this case, squares of the space derivatives of the fields. And it's positive. It's positive because derivative of psi dagger times derivative of psi is positive. Okay, let's take another example of a possible thing in the Hamiltonian and discuss what it means. Now, again, without mathematical proofs, because we'll just belabor points that we've essentially already made, but let's add in here. Let's assume there are two kinds of particles first. I'm not going to give them names. I'm going to call them A and B. You can call them proton and electron if you like. Then first of all, there's the energy of the electrons. So this is the field operator for electrons. It creates and annihilates electrons. It does nothing to protons. This is the kinetic energy of all the electrons. We have to add to that the kinetic energy of all the protons. This is twice m electron. This is twice m proton. And then psi proton of x. Okay, so far all I have is the kinetic energies. Now, I'm going to add something. It's not the realistic, real interaction between electrons and protons. This is just a model interaction. And what I'm going to add is plus the integral over space, integral dx, times the creation operator of an electron at point x times the creation operator of a proton at point x times the annihilation operator of an electron at point x times the annihilation of a proton at the same point x. Yes. Okay. This comes along and it annihilates a proton and an electron if it finds them. Where does it annihilate them? It annihilates them at position x. So if there happens to be an electron and a proton, and let's draw this the following way. This is a space-time diagram. Here's a space-time diagram. Here's time. This is just a way to visualize. This is not to be taken too seriously at the moment. But an electron and a proton are moving around. Here they are. This is time. This is space. These are the world lines of the electrons and the proton, the electron and the proton. If they're not at the same place, then this is not going to give anything if it acts on the state. This will act on a state and will only act if it finds both a proton and an electron at the same place. It doesn't matter what place, because you're integrating over x, you'll get some kind of thing no matter where x is, if there are two particles at the same place. But if there are not two particles in the same place, it just gives 0. Okay, so first of all, it looks for particles at the same place. If it finds particles at the same place, it annihilates the proton, it annihilates the electron, but then it creates a proton and it creates an electron at the same point. It scatters the electron and the proton is what it does. Electron and proton come in, and when they're at the same point, and then they go out, and it scatters them. Is the momentum conserved? Yes, the momentum is conserved for exactly the reason we wrote up there. But are the individual momentums conserved? No, the individual momentums are not conserved. I should have gone through that here. The individual momentums are not conserved. The only conservation of momentum is the overall conservation. So when an operator like this comes along and hits the state of an electron-proton system, it scatters the electron-proton system. So it's a scattering operator. It's equivalent to a potential energy between the electron and proton when they're at the same spot. Of course, real electrons and protons interact even if they're not at the same spot through the Coulomb potential, but we're just taking little steps one at a time. Okay, so if through experiment you discovered that there was an interaction where electrons and protons by a short-range potential, short range meaning it only acts when they're at the same point, scatter each other, this is what you would put into the Hamiltonian. So it's a kind of experimental, a bit of experimental physics to tell you what kind of things the particles can do. And once you know what they can do, you mock it up by expressions like this. Let's do some more. Let's see what else we could imagine having. Another thing we could imagine having.
Question, why is that part of the Hamiltonian? The energy doesn't change, right?
That's equivalent to a potential energy in the Hamiltonian between the electron and the proton.
Oh.
Yeah.
Another question?
But, the question, what Hamiltonians do is change states from one instant to the next. If you discovered experimentally that an electron and a proton over a short period of time will scatter each other if they're at the same place, you've got to say there must be something in the Hamiltonian, the thing which updates the state, which corresponds to that scattering. And that's the kind of thing you would write down. Okay? So when you see in quantum field theory expressions like this, interactions involving products of fields, maybe products for different fields, different kinds of particles, they're representing these basic simple interactions where particles, if they're at the same point, can interact with each other. Another example, supposing experimentally you discovered that particle of type A could decay and form particle of type B and particle of type C. Again, this is time. Read it from bottom to top. Particle A comes along, and you discover that there's a process where particle A disappears at a point, and particle B and C appear at the same point. Okay. You discover in your bubble chamber, you discover tracks which lead you to conclude that A came in, B and C went out, and they came out from the same place that A came in. What would you write down? Well, okay, so you need something to remove the A. What happens over a short period of time is an A disappears, that's an annihilation operator, and a B and a C are created. So let's try that. What kind of thing might we write down? We might write down the annihilation operator for A, for field A, at position X, that's the annihilation operator, and then two creation operators, one for B and one for C. And you'd say, look, I've discovered experimentally that the state of the system changes so in such a way that an A disappears, that's this, and a B and a C are produced. Furthermore, because every point of space is like every other point of space, you would begin to suspect this could happen not only at point X, but it could happen anywhere. So you integrate it over X. Weigh all points of space equally. Once you do this, you can read off from what we talked about over here that the momentum is conserved. The momentum of A becomes the momentum of B and C. Now, energy conservation is a little more complicated, but energy is always conserved, let's put it that way. Okay, so over the long run, anyway. Okay, so this is what else would you put into this Hamiltonian or this term in the Hamiltonian besides these products of fields? How about a number? For example, in both cases, incidentally, I should have said that also in this case over here. There's a possible number, plus G, the coupling constant. The coupling constant is a number, which can be anything. And it can be extremely small if the particles are very weakly interacting. That would mean that even if the particles arrive at the same point, the probability that they scatter is small. And you would experimentally verify this. You would scatter two particles, and you would discover most of the time they don't interact. In that case, G is a small number. If the particles have a large interaction probability, then G is a large number. And G is called the coupling constant. Okay, we're on our way to building quantum field theories. Let me say one more thing about this term here. What goes in the Hamiltonian must be Hermitian. That's a rule. Hamiltonians are Hermitian, and that's equal or equivalent to the statement that the time evolution is unitary. Time evolution is unitary because it's got the conserved probabilities. Okay, so is this Hermitian? Well, it's not Hermitian, it's not Hermitian, and the reason it's not Hermitian is because the Hermitian conjugates of a psi dagger are a psi, and the Hermitian conjugates of a psi are a psi dagger. To make it Hermitian, you must add its Hermitian conjugate. Its Hermitian conjugate is the same operator, except with everything replaced by its conjugate. And you also have to remember when you Hermitian conjugate things, you've got to change the order, but in this case it wouldn't matter. But let's do it anyway. It doesn't matter in this case, because if they're different fields, they commute with each other. So let's, but we can do it, psi dagger A of x times psi B of x times psi C of x. Now, how is this different than this? The answer is every creation operator has been replaced by an annihilation operator. Every annihilation operator has been replaced by a creation operator. And the process described by the second half here, let's look what it says. It annihilates a C and it annihilates a B and creates an A. So it's just the whole thing turned over. B and C come in and A go out. So once you discover that there's a process where A goes to B and C, you can immediately conclude that it must also be the case that if you have a B and a C, they can turn into an A. Okay.
Exception to this?
What's that?
Is there any kind of exception to this? Is there any exception to this?
No. If there is, we don't know about it. Okay, so now we have the basic rules of a simple version of quantum field theory. You have creation and annihilation operators. You have fields made out of them. The fields are functions of position, and they can be thought of as creation and annihilation operators for particles at definite positions. Each type of particle has its own field. And you write down Hamiltonians. The Hamiltonians always contain, or typically contain the kinetic energies of the particles. That's the top thing there. And then, in addition, various other concoctions, which, let's put it this way. In the first round of particle physics, those concoctions largely came from experiment. Well, electrodynamics, of course, came from a little more than just experiment. But a classic example is the theory of beta decay. The theory of beta decay is a neutron decaying into a proton, an electron, and a neutrino. Okay? Proton goes to electron, and so forth. All right, so what would you write there? Then you would have four operators. This would be annihilate a neutron, create a proton, create an electron, and create a neutrino. Let's go one step further. when I wrote that psi of, well, state vector, phi of t plus epsilon is equal to phi of t minus I h bar minus I epsilon h times phi of t. This, of course, was an approximation. It was an approximation to leading first order in small quantities, namely epsilon. What would happen if I made epsilon a little bit bigger? Well, there would be a next term which would be order epsilon squared. Do you know what it would be? It would be minus epsilon squared over 2 times h squared phi. This is just another way of saying that if, well, it's the Schrodinger equation. The Schrodinger equation gives you the derivative of psi proportional to h times psi. But it can also give you the second derivative of psi, and that's proportional to h squared times psi. So this is what you would learn if you went to the next order in small quantities, that in the next order in small quantities, there's a change in the state from one instant to another which is proportional to h squared times psi. That's very interesting because, for example, one of the things it would say, we can draw some diagrams now. What does h squared do? Well, we could take h squared and multiply it all out. Okay, and we could try to see what it does. But that's dumb. The easy way to do it is just to use the pictures. We take the pictures. Let's erase this. And the pictures say that in lowest order, a thing which can happen is B and C can come together and make A. That's just the Hamiltonian itself, or this term in the Hamiltonian. But supposing the Hamiltonian acted again on this, well, here's another term in the Hamiltonian. The same term can act twice. Whoops, this is wrong, B and C. But this term can't really act twice, because for it to act twice, it has to find, the second time, it has to find a B and a C again. Well, in the first round here, the B and the C were eaten, no B and C, so this term can't act successively twice. But what can happen is when you square the Hamiltonian, you can get this term times this term. In other words, let's write it out. It's got psi B, psi C, times psi dagger A, and then psi dagger A, then psi A, psi B, psi C. A big mess. That's the square of a term, or a piece of the square of the term of the Hamiltonian. But it's very easy to see what it says. It says it takes a B and a C and it makes an A, and it takes a B and a C and turns it into an A, and then it takes the A, annihilates the A, and puts back a B and a C. The effect of this is to contribute or to create a scattering between B and C. The A, that's just temporary. The B and the C came in, they annihilated to form A, and A then converted back to B and C using the same Hamiltonian. So it's not just that the Hamiltonian updates the state. All the powers of the Hamiltonian give you a vast variety of different processes that can happen that contribute to the amplitude for scattering. This is the amplitude for scattering. B goes to C. And the only rule, at least the only rule we've set up till now, is that momentum is conserved, total momentum. The momentum of C can change, the momentum of B can change, but in going from beginning to end, the total momentum should be the same. Okay.
Should that psi sub C on the left, should that have a dagger?
Possibly, yes. Right. Right, so you see, once you learn this little piece of information, oh my goodness, all sorts of other things can happen. Well, we now know what did I just do? I erased A and B goes to C. Good. Here's something else that can happen. A can come in, create B and C, but now if there happened to have been another B around, let's suppose there was another B around to begin with. Yeah. This says that if B finds a C to annihilate with, then it can make an A. So again, in the second order of the Hamiltonian, where you iterate the Hamiltonian twice, you not only get processes in which A goes to B and C go to A, or that B and C go back to B and C, but now you have a scattering amplitude where A and B scatter with each other, with the exchange of a C. This is called an exchange diagram. It looks as though you're drawing a picture where a C jumps over from here to here. All it is a contribution to the scattering coming from the Hamiltonian twice, acting twice. So in following the evolution of the system, when the Hamiltonian acts twice, the first time it can take an A and a B to C, leaving this B over here alone. This is a different B. Leaving it alone, not doing anything. And then the second power of the Hamiltonian can take C and B and convert it back to A. So you see, once you have these simple terms in the Hamiltonian, you have a vast forest of many, many different kinds of interactions that are mediated by the same simple term in the Hamiltonian. That's why quantum field theory is powerful. A small number of terms in the Hamiltonian can lead to a huge number of different reactions, all related by having the same form in the Hamiltonian, the same coupling constant. For example, the coupling constant, yeah. If there's a coupling constant governing a term in the Hamiltonian here, then when you square the Hamiltonian, you might get the coupling constant squared. In fact, you would here. Each one of these vertices, these are called vertices, they carry a coupling constant in the Hamiltonian. So this process would have a coupling constant squared in front of it. So this would correlate an enormous amount of data about all of the possible interactions of A's, B's, and C's. And there are many, of course. This is the most common thing in the world in particle physics, is to be studying those correlations. Yeah.
So so I assume you can have A decaying into B and C, and then B and C coming back together to form an A. But what is that?
Sorry, say it again now. Oh, A going to B and C, and then B and C coming back together. That's a self-energy diagram for an A. It changes the structure of A. What it tells you is that a real A particle that you might measure in the laboratory has a probability to be not just an A, but to be a B and C close to each other. So what it means is that if you found an A in your laboratory and you scattered something off it, with some probability you would find that that A behaved as if it were a B and a C together, close together. So for example, in electron, one such process, one example of this would be an electron emitting a photon. Electron comes in, electron goes out, emits a photon. Okay, so the operator for that would be psi dagger electron. Sorry, psi electron that annihilates an electron. Psi dagger. Create an electron, and then a photon creation operator. Photons, the photon field is called A, all at the same point. So it absorbs an electron, creates an electron, and emits a photon. Okay, so one of the things that can happen, as Kevin points out, is you can have the electron moving along, becoming an electron, emitting a photon, and then the photon coming back and becoming an electron. Now, don't take too literally the statement, this happens and then that happens and then that happens. This is really just standing for a term second order in the Hamiltonian, iterating the Hamiltonian twice. But it's clearly very tempting to try to describe this by saying a sequence of things happen. Now, of course, if you go into the system and look and see whether that something happened, you screw up the whole thing, as usual in quantum mechanics. So, but what this does tell you is that if you scatter another electron off the first electron, you will find some of the time that this electron contains a photon. That what you thought was a single electron really looks like a composite of an electron with a photon. The probability to find the photon there is small. It's about 1%, but that's what it says. So it really should be thought of as a correction to the structure of the electron rather than a new process. It only becomes a new process when you interfere with it and you look and see what's inside, and some of the times you will find that what's inside contains a photon. Of course, what will happen if you look for the photon, you'll discover the photon some of the times, you'll scatter the photon out, and you'll completely screw up the electron. You'll excite the electron, and things will happen.
At that first vertex, are both energy and momentum concerned?
No, only momentum. Only momentum. Right. And as I said, these things are not literally happening. They're shorthands for the mathematics, in this case of just squaring the Hamiltonian.
So what actually happens is a superposition of all possible things.
Yeah.
And so that's why the energy
Yeah.
of any individual one need not be conserved.
Yeah. And there's all kinds of, don't forget, there's all sorts of terms in the energy, and counting up all the energy, don't forget to count up these interaction terms. So the energy isn't just the sum of the energy of the particles, but that sort of gets hidden in these pictures. That missing energy that's in the interactions, you might say, allows the pictures to violate energy conservation at each vertex. But, you know, if you get confused, you just go back to where it came from. It came from the Schrodinger equation going for second order in small quantities. And that's what it means. Now, we're not going to do Feynman diagrams in their full-blown glory, but this is where they come from, and this is where the rest is just technology and tricks to calculate things with. But this is the basic physics of it, yeah.
I was just thinking about the electric field of the electron there.
Well, this, good. This is the electric field of the electron.
Well, that's what I was going to ask about,
Yeah.
because it seems to me that, at least in a literal sense, I mean, it seems like the field, the presence of field at some distance, isn't literally created by radiation.
Say it again?
It's not, you could say that the propagation of the field ahead of the electron obeys the same wave equation as radiation would, but it's not literally the radiation.
No, it's not literally the radiation, although if you take a very high energy electron, 1% of the time it behaves as if it were a real electron and a real photon. That's because photons move at the speed of light. These photons are clearly not going to move with the speed of light. It's got to go from here to here, and the electron is not moving with the speed of light. So literally thinking of these as photons moving around is not going to work. But if the electron itself is moving with the speed of light, or close to it, very close to it, then it really does behave as though it were a superposition of an electron and then an electron with a real photon, with a genuine photon.
I'm actually thinking of things where the electrons are moving rather slowly.
Yeah.
And the field is moving very quickly as a wave ahead of it. And then,
Well, then you're going to get yourself completely confused trying to form a model for what's going on.
well, I'm just saying, it's not literally
Right.
creating real photons
It is not.
to fill the field.
Right.
Right, okay.
Right. And don't try to create a mechanical model of what's going on. It won't work.
No, but there's effects like self-interference in the two-slit experiment, self-interference of a single photon, okay?
Was that
The-
me? I don't know.
You have to have sort of the wave version of the photon, or I mean, you know, the meets up with its own field, right, coming through.
Well, it has nothing to do with this, though.
Well, it was related to my question. And you have the Aharonov bone experiment so that, you know, the field is present where, you know, it's not really radiation.
Yeah, no, this is not the radiation field. This is the induction field. Right, but as I tell you, when the electron is fast, it can be thought of as a radiation field.
Can you finish your thought you were starting to say about,
Lost it. It's gone. It's finished.
you were starting to say that if you try to create a model of this, it will fail.
Well, you'll try to create, you know, your brain is always trying to create classical models, classical pictures for things. You can get some experience doing some calculations, and after a while you know how to deal with these diagrams, and you start to give some literalness to the diagrams, which really is not really right. It's just a mathematical trick to calculate h squared, h cubed. Basically, we're calculating e to the I ht by expanding it out in powers of h, right? E to the I ht is the time development, and that's what we're expanding out here. 1 minus I epsilon h minus epsilon squared over 2. This 2 is the 2 of the exponential expansion. What's the next term? I guess it's plus I epsilon cubed, h cubed over 3 factorial. Right. Now, how do you actually calculate the probability of a given scattering? That, of course, requires some technology, which we haven't done. But, okay.
So somehow, and I imagine we're not going to be seeing it tonight or next week, this mechanism, if you do the right mathematics with this mechanism and you have an electron here and an electron here, you can somehow show the Coulomb attraction as the classical limit
No.
of this process.
Yes. But the way you would do it, the simplest way to do it, well, yes, the answer is yes. But it's not literally that a photon jumps from one place to another. No. That's a little bit too simplistic, yeah.
Are the coupling constants calculated from first principles? Or are they not?
No. Sometimes relationships between coupling constants can be calculated from symmetry principles, but generally the coupling constants are basically experimental input. It's disappointing, isn't it? Yeah. On the other hand, think about what happens when there is a relation between coupling constants that's dictated by the mathematics, some symmetry principle. Then it relates two otherwise independent and different reactions. When that happens and you go in the laboratory and you discover that the reactions behave according to the way the coupling constants, which have been determined from first principles, tell you they're supposed to behave, that's exhilarating. Doesn't happen very often, but happens. Does happen.
Difference between an accidental symmetry.
Yeah. Accidental symmetries are accidents, and they usually don't tell you very much. Gauge symmetries are the symmetries which tell you something. Okay. Well, I take back what I said. Accidental symmetries also tell you things. Important things. We're going to, I had promised to start fermions today, and I'm going to. But instead of talking about fermion fields, which we'll come to next time, let's talk about the Dirac equation. Let's start the Dirac equation today. From one point of view, the Dirac equation, first of all, that means we're entering into relativity theory. We're using relativity theory. Thus far, what we did was to study non-relativistic second quantization. Now we want to move on a little bit and study the relativistic electron. We're going to begin with a one-dimensional electron, an electron only moving in one dimension. The simplest possible theory of an electron. It's not a realistic theory. Electrons move in 3 dimensions, but it's the easiest place to get started. Without having to throw a bunch of formulas and a bunch of symbols, we can study the one-dimensional electron and learn quite a lot without getting spurious complexity because of the 3-dimensionality of space. Then we come back to 3 dimensions. 3 plus 1, 3 dimensions, right? Okay, so the electron ought to have a Schrodinger equation. Particles should have Schrodinger equations. On the other hand, it shouldn't be, if we're dealing with relativity, incidentally, the reason why we deal with relativity when we deal with electrons is because electrons are pretty light. They move around, and of course, in an accelerator, we can get them up to essentially the speed of light. But I'm thinking now back to the age of Dirac. Why would Dirac have bothered using a relativistic theory, other than curiosity, perhaps, about how relativistic electrons work? And the answer is that in an atom, and particularly in a hydrogen atom, the electron moves with an appreciable fraction of the speed of light, about 1% of the speed of light. So relativity is an important correction to the motion of an electron. If you take heavy atoms, where the inner electrons are closer to the nucleus, they are really moving, and they can be pretty close to, they're not moving with the speed of light, but they can be moving with even more appreciable velocities. So if you want to get atoms right, not just to 0th order, you want to get the corrections to atoms right, the important corrections are relativistic. So now, whether Dirac was motivated by that fact, or he was just motivated by curiosity about how to make relativistic Schrodinger equations, I don't know. Okay, we begin in formulating the idea of a Schrodinger equation for a particle. We begin pretty much with a classical relationship between energy and momentum. We start with energy as a function of momentum. Now really, of course, we should go from quantum mechanics to classical mechanics, because that's the logic. But what we tend to know about is classical physics, and so we usually go in the other direction. And for an ordinary non-relativistic particle, the energy, which I'll call a Hamiltonian, or let's call it E, but remember it is the Hamiltonian, it's E equals p squared over 2m. That's the energy as a function of momentum. And then to go to quantum mechanics, we replace energy by Hamiltonian, which we then replace by I d by dt. In other words, the Hamiltonian is a thing which gives you the time derivative of the wave function. That's on the left side. And on the right side, we replace p by minus I d by dx. And that gives us the Schrodinger equation. d psi by dt, or I d psi by dt, is minus d squared over 2m, second derivative. You know the story. Schrodinger equation. Okay, so Dirac said, why don't I do the same thing? What's the energy as a function of momentum? Oy, it's ugly. Square root of p squared plus m squared. Let's write down, because we'll need it later, the relation between energy and momentum. E squared equals p squared plus m squared. Now I've set the speed of light equal to 1, and I will do so continuously throughout. Speed of light is equal to 1. E squared is equal to p squared plus m squared. From this, you can write down immediately an equation. If you take E to be I d by dt, then what is E squared? It's the second derivative with respect to t, minus the second derivative with respect to t. So you would write down minus second derivative with respect to t squared, that's E, on some phi of x, or psi of x, some wave function, equals p squared, that's minus d by dx squared, psi, plus m squared psi, or phi, whatever, phi, psi, I don't know. Doesn't matter, whatever we call it. The wave function of the electron, or the wave function of something. Anybody know what the name of this equation is? I seem to have, yeah, that's right. Yeah, that's right. That's the Klein-Gordon equation. And you might say that Dirac, why didn't he do this? I don't know why he didn't do this. He had an argument. His argument was, look, we're supposed to write, according to my principles of quantum mechanics, which are in my textbook, we're supposed to write I d by dt is equal to h times psi. We're not supposed to have to square the second derivative. I don't want to know what the what h squared is. I want to know what h is. That's what I wrote in my book, and I'm going to stick by it. Okay? So he wants an equation that reads I d, let's call it psi. Now it's not a field operator, it's just a wave function for an electron, by dt is equal to some h, some operator on psi. What kind of an operator? Well, it's got to have the momentum, it's got to have the mass. He could just put here the square root of p squared plus m squared, and then write, okay, then he could write the following strange equation. Is equal to square root of p squared, which is minus d by dx squared, plus m squared psi. What on earth does that mean? What does the square root of d by dx squared plus m squared mean? It doesn't mean very much. Well, you can give it some technical meaning, but it's pretty horrible. It's not a nice, the square root of a differential operator like this is not a nice thing. So I think that Dirac just backed away from it and said, I don't like that. I don't like that. I don't have a convincing case against it, but I'm going to start over again. I'm going to start from the beginning. And here's what he said. We'll do it in the one-dimensional case, and then we'll come back to. Let's start the one-dimensional case with a massless particle, a particle with no mass. An electron that doesn't have a mass. And we'll put the mass back in and we'll see how that works. Right. So, here's what you know about a particle moving along the x-axis with the speed of light. It's massless, so it moves with the speed of light. Its momentum is equal to its energy. Strictly speaking, if I put the speed of light back, it would go over here. Energy is equal to c times the momentum. This is true for a photon. It's true for any massless particle. Okay. This is a massless particle moving to the right. What about a massless particle moving to the left, incidentally? Yeah, p would be negative in that case. P would be positive if the particle moves to the right. If the particle moves to the left, then P is negative, but clearly the energy should still be positive, so we would have to write P equals minus E. Well, we only get to write one thing. We don't get to write both. So let's start with P equals E and content ourselves with studying a particle moving to the right. Okay. So we know what this says. We've actually studied this equation. This equation, if we now say that E is equal to the Hamiltonian, and Hamiltonian is I d by dt, this says I d psi by dt, that's h psi, is equal to P times psi, and that's minus I d psi by dx. That's a pretty simple equation. D psi, what does it say? It says d psi by dt plus d psi by dx equals 0. What are the solutions of such an equation? No? They're functions of x minus t. Any function of x minus t will satisfy this equation. A function of x minus t is a wave which is moving along the axis to the right with the speed of light. Speed of light now being chosen to be equal to 1. Any function of x minus t, psi is a function of x minus t. That means it describes a wave moving to the right, a rigid profile. Profile doesn't change, but the location of the center of the wave changes, and it moves with the speed of light. Okay, this is a fine equation, very nice. 2 things wrong with it. 2 things, and they're unrelated things. They're unrelated, they're not the same thing. The first thing that's wrong with it is it's got negative energy. What if the momentum is negative? We're allowed to have negative momentum. Momentum is a observable which can be positive or negative. It's negative if it's pointing along the minus x-axis. It's positive if it's along the plus x-axis. It's got particles of negative energy with negative momentum. This sounds very dangerous. It sounds like we can take those, we can just keep filling up the world with more and more negative energy particles, lowering the energy, lowering it without bound from below. That's a pretty dangerous situation. We don't want that. So first problem with this is it contains particles of negative energy. We've got to fix that. The second problem with it is it only has particles which move to the right. Okay. Well, we could imagine a theory of particles that only move to the right, but it wouldn't look like, it certainly wouldn't look like garden variety electrons. We don't know any particles that only move along one direction. If it can move to the right, it can also move to the left. So that's another thing we can try to fix. Okay, so here's what Dirac said. He said, in effect, it's not exactly what he said, but in effect he said, let's take 2 species. This is to get rid of the left-right story, not the energy story. To get rid of the left-right story, he said, let's take 2 species. Let's call it psi 1 and psi 2. 2 species of electrons, one of which we'll think of as the species of electrons which move to the right, and the other we'll think of as the species of electrons which go to the left. And let's just write down 2 separate equations. Let's call them, and think of 2 separate kinds of particles. Or we can say a particle can be one kind or the other. If we have only one particle, it could be the right kind or the left kind. And so let's put a psi 1 here. This is the equation for particles which move to the right. And what about the equation for particles to move to the left, which we'll call psi 2? That's the equation psi 2 by dt minus d psi 2 by dx is equal to 0. Now, in quantum mechanics, of course, if you can have a particle of type 1 and a particle of type 2, you can have a linear superposition of them. So you can have particles which have a probability, a half, for example, of moving to the left and a half of moving to the right. But these are the wave functions of the two kinds of particles. So Dirac next said, look, it looks to me like what we're talking about is a particle with a degree of freedom, an extra degree of freedom, not just x, not just the coordinate position, or equivalently the momentum, you can trade one for the other, but it looks like it has a discrete thing, a plus oneness or a minus oneness, sort of like a spin. It's not a spin, but sort of like a spin. It can either be up or it can be down. Up in this case means traveling to the right, down means traveling to the left. So he understood a little bit about matrices and so forth, and he said, look, let's write this in matrix form. Let's introduce observables which tell you whether you're 1 or 2, and that means that what we want to do is take our psi's and think of them as a column vector. Psi 1 and psi 2, put them together like so. This is the amplitude that the particle is right moving. This is the amplitude that the particle is left moving. And let's introduce matrices. In particular, let's introduce a matrix whose eigenvectors are 1 or 2. In other words, 1 or 2. Here's a matrix which the eigenvectors are 1 with eigenvalue 1 and minus 1 with eigenvalue 2. So here is an observable which distinguishes the two kinds of particles. It's either up, well, it's not up or down, but it's moving to the right or it's moving to the left, and we'll just give this matrix a name. Now, if it was spin, and it's the observable, it is the observable, the matrix observable or the operator, the linear operator, which distinguishes between the two kinds of particles. Okay? It's very much like a spin being up or a spin being down, except that it's not spin. Okay, this matrix has a name. Anybody know what its name is? I forget. No, I don't. It is sigma 3. It's a Pauli matrix, but it's a Pauli matrix in the context where we're thinking about spin, and spin has to do with angular momentum. It's just not that here. All right? It's just a different thing. Dirac called it alpha. He called it alpha, so let's call it alpha. And it's exactly that matrix. And then he wrote, when I'm saying he did this, he actually didn't do this. He plunged right in and did it in 3 dimensions. But I don't know, for all I know, maybe he did do this, but
It might make a different kind of sense in 3 dimensions. I mean, you have the direction, a vector type direction.
yeah. Right, it does. But if he were doing it in 1 dimension, which is the easy baby way to get started, and it's not so baby, it's correct, you would write that H instead of the Hamiltonian, instead of E is the Hamiltonian, but now we're thinking of it as a Hamiltonian, not just a number. The Hamiltonian is P if the particle is moving to the right, and minus P if the particle, the two kinds of particles, one move to the right, the other go. So it's P if it's a right mover, and minus P if it's a left mover, but the right movers and the left movers are distinguished by alpha. So we can summarize it by just writing H equals alpha P. If alpha is +1, it's a right mover. If alpha is -1, it's a left mover. So it puts together into a single structure a particle with a degree of freedom, which is its position, and another degree of freedom which is its alpha. puts it together, and says H is equal to alpha P. This now becomes a equation. You can write it in a number of ways. Here is one way of writing it. But we can also write it as I d by dt of psi 1, psi 2, a two-component column vector, is equal to alpha, which is the matrix 1 minus 1, 0, 0, times minus I d psi by dx. Let's put the minus I over here. Or? Yeah, I'm sorry. D by dx, good. D by dx of psi 1, psi 2. Or we can just condense it. We don't need all of this stuff. We can just write I d psi by dt is equal to minus I alpha d psi by dx. But remember that psi is this two-component column vector. They all are the same thing. Keep in mind that, and since alpha has both positive and negative eigenvalue, this describes both right-moving and left-moving waves. Okay, so by the trick of introducing the Dirac matrix alpha and a two-component structure for the wave function, we now have cured the problem of the one-way street. It's now a two-way street, and an electron can go either to the left or the right. I said there were two things wrong. The first I said was the negative energy. We still have that. The second was the one-wayness. I forgot a third one. So far, the electron has no mass. This is something moving with the speed of light. Okay? This is not what we want. We want an electron which moves with less than the speed of light. In other words, we want an electron with a mass. Okay? I think I could have done this. It took the genius of Dirac to make the next step. He said, here's what he said. Well, he said, let's just add a term to the Hamiltonian and see if we can get it to come out to be a mass. I'm going to add something here. It ought to be proportional to the mass. M, of course, means mc squared, strictly. It's the energy of a particle at rest when it has no momentum. So we want something to account for the energy of a particle when it has no momentum. But since all of these equations now are acting on these two-component columns, in general, this thing has to be a matrix. It's got to be something which can act. It could be the unit matrix for all I know, but let's not prejudice it. Let's add something here proportional to the mass, and let's introduce another matrix, and let's call it beta. Okay. Now here, I have a feeling I probably would not have caught this. Dirac did, and moreover, caught it in 3 dimensions, which is a little bit harder, but not much. Okay, so this is some operator. It's a genuine operator. P is the momentum operator. Alpha is the alpha operator. Beta is some operator which has only to do with the two-componentness. It doesn't have to do with X. It doesn't have to do with P. It just acts on the two-component spinners. We'll call them spinners for what they are. And here's what he said. He said, look, here's what I know. I know that in a relativistic theory, the energy squared, which is the Hamiltonian squared, should equal p squared plus m squared. Let's insist on this. Let's insist on this. Let's insist that when I square this, when I square h, that I get p squared plus m squared. So let's see what that says. All right, so that says h squared, which is e squared, should equal alpha p plus beta m times alpha p plus beta m. Okay, first of all, I'm going to get a p squared term. It's going to be alpha squared, oh, incidentally, alpha commutes with p. It acts in a different tensor product Hilbert space. We don't have to worry about commutation between alphas and p's. Okay, the first term is alpha squared p squared. That looks good. We want to get p squared. We got alpha squared p squared. It's easy to deal with. Let's just insist that alpha squared be 1. But wait a minute. We already know what alpha is. Alpha is this matrix over here. Its square is 1. So we're in good shape with a p squared term. That's good. If we use the fact that we know what alpha is, then this is just p squared. How about the m squared term? There's another term which is beta squared m squared. Well, I don't know what beta is yet. I haven't decided what beta is yet. But what do I know? I know that beta squared should be 1. So let's write down what we know. Alpha squared equals 1. That's good. We have that already. Beta squared equals 1. There's lots of matrices around whose square is equal to 1, so not to worry. Any one of the Pauli matrices, its square is equal to 1.
1 means identity matrix, right?
1 means the identity matrix, yes. Any of the Pauli matrices, its square is equal to 1. The identity matrix itself, its square is equal to 1. Okay, so we've taken care of that. But now, this is p squared plus m squared. But then we have an extra term. And the extra term is alpha beta. It's a product of p with m. And it's got one term which has alpha beta and another term which has beta alpha. So it has alpha beta plus beta alpha times pm. We don't want that term. That term is something we don't want. So they should anti-commute. So we want that alpha beta plus beta alpha is equal to 0. And once we do that, then we have our cake and eat it. We first of all have an equation of this very simple kind that Dirac liked so much, namely, where is it? H on psi equals d psi, I d psi dt, for one thing. And we also have that E squared equals P squared plus M squared. All we have to do is find a matrix which anti-commutes. That means when you change the order, the sign changes, which anti-commutes with alpha. Now, Pauli had already invented his matrices, and Dirac, had he done things this way, would have instantly recognized that this happens to be one of the Pauli matrices. And he also would have known that any pair of the Pauli matrices anti-commute. So he could simply take for beta any other of the Pauli
In
matrices.
practice, he took those equations that you wrote down and just said, well, that he already knows the Pauli matrices do that.
Yeah.
Yeah.
Yeah. He did have Pauli to back him up on this. I mean, Pauli had already done lots of work with these.
He just used unknowns here. He just used unknowns.
He did. Yeah, he did. But then he said, let's find some matrices which do this. All right, so in this case, we have a choice about beta, but let's resolve that ambiguity. It's not a real genuine ambiguity. It's a convention. But here's in the second matrix, beta. This is alpha, and this is beta, namely 0, 1, 1, 0. You can go home and check that alpha times beta is minus beta times alpha. I'm not going to do it on the blackboard. It's a straightforward thing. They do anti-commute, and so Dirac now had his equation, and let's see what it says. Let's see what kind of equation he had.
It's not Einstein's beta, right?
What's that?
It's not Einstein's beta, right?
It's not what?
The relativistic beta.
No, it's a matrix. It's a Pauli matrix. No, it's not, definitely not that.
We just don't have enough letters.
Yeah. I'm following Dirac's notation. Alpha and beta are called Dirac matrices. In this case, they're 2 by 2 matrices. We'll find out probably next week that you can't do it with 2 by 2 matrices in 3 dimensions, but we'll do something else. Okay, so let's see what this says. This says, where was our equation? It says I d psi dt, where psi is a 2-component spinner, is equal to alpha p times psi plus beta m times psi, where m is the mass. Okay, let's write it out. As a 2-component equation, this is I, and in the first slot here we would write d psi by dt. So, well, let's write it. I d by dt, psi 1, psi 2. And this stands for a column made out of I d psi 1 dt and I d psi 2 by dt. Then we have alpha, and alpha is 1 minus 1, 0, 0, times p, but p is minus I d by dx. So we have a minus I equals minus I d by dx of psi 1, psi 2. Now, so far, we're just rewriting the 2 equations here. We're just rewriting these 2 equations, separate equations for psi 1 and psi 2, and the reason they're separate is because this matrix is diagonal. It does not mix psi 1 with psi 2. But then we have beta, and so let's add plus beta, and beta is 1, 1, 0, 0. We have to multiply it by m, so let's put the m right in here, m right in here. Psi 1, psi 2. If we write out this term, we'll find that the upper, because the psi 1 is off diagonal, sorry, because the beta is off diagonal, what does this do? It switches psi 1 and psi 2. So this term here just becomes m psi 2 psi 1. So let's come back to this equation over here. What it does, I'll never get the I in the right place. So yeah, let's put the I in the right place. I minus I equals, and now it looks like this one is m psi 2 and the other one is m psi 1. So you see, once you introduce the mass term, the 2 components are not independent anymore. They interact with each other. The equation couples one to the other. And what does that coupling do? It gives the particle a mass. And if you work out how it moves slower than the speed of light. It moves as if it were a particle with E squared equals P squared plus M squared. In other words, a relativistic particle of finite mass. This is what Dirac did to get rid of the left-right nonsense and at the same time to get a mass. Now, I suspect he knew something else, that the mass was connected with the left-rightness. If you have a particle which is massless, it's consistent to just think that it can only go along the right, in one dimension, that it only goes in one direction. And the reason is because any Lorentz transformation of a particle moving to the right is still a particle moving to the right if it's moving with the speed of light. A Lorentz transformation will not take a particle moving to the right with the speed of light and convert it to a particle moving to the left with the speed of light. Okay? So particles which move with the speed of light, the left ones and the right ones don't talk to each other through Lorentz transformations. If a particle has a mass, you can bring it to rest. Or you can, you can maybe not bring it to rest, but you can bring it to some finite momentum along the a finite velocity along the x-axis. So it's moving with half the speed of light this way. And then you get on your horse and run with 3/4 of the speed of light. It is now moving in the opposite direction. So it's just not possible to have a massive particle which only moves to the right. So Dirac knew, again, I imagine he knew, that the left-rightness was coupled together with the mass issue, and that by fixing the left-right issue, he could potentially create a mass for the electron. Yeah.
Is this in some sense a chiral oscillation?
What's that?
Is this in some sense related to chiral oscillation?
The left-rightness is called the chirality in this case. It means handedness. In this case, the,
Swapping of 2 and 1 is what I'm thinking.
yeah, no, in this case, the handedness is just the alpha matrix over here. It's not a swap, but it's the mass term which is the swap.
Yeah, I was just talking about the full equation. Is there chiral oscillation built into that?
Yeah. The mass term is the chiral oscillation. Yeah. Yeah. Oh, absolutely. Yeah.
Why should a fermion equation come from the square root of a boson equation?
No. This has nothing to do with fermions or bosons. E squared equals p squared plus m squared for any relativistic system.
Yeah, as long as it's not massless.
E squared is equal to p squared plus m squared. That has nothing particular to do with whether it's a, every particle satisfies that. Right. So it's true you can sort of think of the Dirac equation as a kind of square root of the Klein-Gordon equation, but I don't think that's particularly helpful. All right, so the last thing we have to do is get straight.
D minus m, d plus m factorization, which is sort of left movers, right movers.
All right, so we have two things to do with the Dirac equation. One is to understand how to get rid of the negative energies. This has not gotten rid of the negative energies. Now we have negative energy right movers and negative energy left movers. We made it worse. And the other is to get to three-dimensional space. But that's easy.
You just pointed back and you said the Dirac equation. Does this pair of equations constitute the Dirac equation?
For the one-dimensional case. Yeah.
Yeah, this is a really long version of the Dirac equation. The usual equation.
No. The Dirac equation would be written this way. I d psi by dt is equal to minus, is equal to, minus I alpha d psi by dx plus beta m psi. That would be the Dirac equation written in one form. You can also write it another way, which is also these days more familiar. You multiply both sides of the equation by beta. And you write let's come to it next time. It's enough for tonight. It's enough for tonight. There's a more symmetric way to write it, which is pretty and the standard way to write it, but it doesn't add anything at this point. Good. Okay, we're finished.
For more, please visit us at stanford.edu.